כאילו, עשיתי אותו כבר בפרוקסי.
סליחה?
לא, אני לא יודע אם אני, כאילו, אולי לא הייתי
אתה יודע זה לא אין פחות אחד.
מה זה?
זה לא אין פחות אחד.
לא,
כן? זה לא רק האחרון, אתה לא חייב להגיד?
למה שזה יהיה דבר מוזר כזה?
לא יודעת, זה משאלה.
מבחינתי תמיד אין פחות אחד. unless indicated otherwise.
Okay, good afternoon. Okay, we continue to discuss neural decoding and specifically linear decoding. So, this is a title. So we have some observations Ni, and we want to, whose statistics depend on some parameter, and we want to decode the parameter based on these observations. So in linear decoders, we will consider two situations. One is discrimination. So maybe I should add here that we might have some P of Ni given some parameter theta. And so in discrimination, we want to discriminate between theta 1 and theta 2. And the form of our discriminator will be a Heaviside function of some linear combination of the observations. And second, we will discuss estimation, where our estimate for theta will be some linear combination of the observations. Okay, so let's start with discrimination. You can copy all this because we will discuss it in the next in a few weeks. So instead of developing a general theory for optimal discrimination, which I will just highlight and will not do explicitly, I want to start with an example. And the reason for the example is that you might wonder whether why are we discussing linear decoders? So one of the reasons is they are simple, and it's a simple architecture which is Who's taking notes? Is anyone volunteering? So we can do another round. I don't know. We will not negotiate right now. Okay. Happy with. Great, thanks. Okay, so I started to say that one thing, it's simple and it's somehow in line with what neurons, simple things that neurons can do, sum their inputs linearly and maybe apply to it some nonlinearity. But I want to highlight through this example that in some situations the linear discriminator is more powerful than you might imagine. So the example will be Poisson neurons. So independent Poisson neurons, which is an important example that we have been discussing already in previous contexts. So we imagine that the mean number of spikes that neuron I emits is some function of theta. This is the tuning curve. And the variability is Poisson. So we can write down explicitly what is the probability for this given theta for this neuron to emit n spikes. And so, and the neurons are independent, so the log of the probability of a certain set of spikes given theta is a sum over all the neurons because they're independent. So the log, the probability is a product over all neurons. The log probability is the sum over all neurons. And for each neuron, we just write the log of the Poisson distribution. So the Poisson distribution has e to the minus lambda to the n divided by n factorial. So when we take the log from the e to the lambda, in our context, the mean is fi of theta. So when we take the log, e to the minus lambda gives us minus fi of theta. And then lambda to the power n, when we take the log, gives us ni log fi of theta. And then we divide by n factorial, so I need to subtract here ni factorial. Log ni factorial. Okay, so that's the probability distribution. And as we already discussed, one way to write the optimal discriminator will be the one that minimizes the probability of error under an assumption that that's two stimuli, theta 1 and theta 2, appear with equal probabilities, is a maximum likelihood discriminator. And one way to write it would be to calculate delta log L. So let's call this L. To calculate delta log L, which is the difference between the likelihood of the observations given theta 1 and theta 2. So let me see if I used, okay, I defined it in my notes like this. So this is defined as a log P of the observations given theta 2 minus log P of the observations given theta 1. And so if this is positive, the optimal discriminator should choose theta 2, and if it's negative, it should choose theta 1. But note that when we now we plug this in, we get a very simple expression. So first of all these expressions which do not depend on theta, they're the same for theta 1 and theta 2, just fall, right? And here there is a dependence on theta, so we'll get two types of terms. One, let's start with this one. So we'll have a sum over all the observations, or the neurons, sum over ni. And now the difference of log fi of theta 2 minus log fi of theta 2, which I can also write as log of the ratio of fi of theta 2 divided by fi of theta 1. And then we have these terms, which look like minus sum over I, fi of theta 2 minus fi of theta 1. So what did we get? We get a linear discriminator, right? It's the dependence of this quantity on the observations is linear, right? And we have here explicitly what is the coefficient at which is used for each observation, and what is what I called here B. So the maximum likelihood discriminator for Poisson neurons, for discriminating between two stimuli, is a linear discriminator. And this is an important conclusion. So theta of the optimal discriminator is theta of delta log L, and it's a linear discriminator. Now, there's another approach that we could have taken for this problem, which is more general. I discussed here specifically the case of independent Poisson neurons, but more generally, if we have a set of observations, we could take a different approach, which I just want to highlight. I will not do everything in detail. So we could have said the following. This is a structure of our discriminator. Let's call this quantity X. Once we fix the weights and we fix the B, this is some function of the observations, right? So X is sum over I, Wi, and Ni plus B. It's a function of the observations. And we can ask ourselves how this X is distributed. So this X is a random variable for each observation, and it has a certain distribution for when theta is equal to theta 1. So well, let's call this P1 of X is P of X given theta 1, and we can do the same for 2. So X has a certain distribution. Again, if theta is theta 1, and it has another distribution if theta is theta 2. And clearly, once we've set up these weights and these weights in B, in principle, our best choice is to do a maximum likelihood decision on X. So we kind of converge all our inputs into one variable, which depends on all of them. And then, if that's all we know, that's all the discriminator is allowed to. The discriminator is only allowed to make its decision based on this linear combination. We can say what we need to do is to ask, if now I tell you what is X, you should ask yourself, is set X more likely given theta 1 or more likely given theta 2, and that's how you want to base your decision. So now the question is whether we know how to describe the distribution of X. And under certain conditions, we know how to do it. So when we have many independent observations, X becomes distributed normally, like a normal distribution. There are some subtleties in this statement. So if we have many independent Poisson neurons, it will be true. Strictly speaking, it also depends on what are the receptive fields of all the neurons. So suppose, for example, that you have a larger number of neurons that all have the same receptive field. Then clearly X is a sum over many independent variables that have the same distribution, and we know that under these conditions, a variable becomes normally distributed. Another situation where we know that X will become normally distributed is when we take the limit where the Fi of each neuron becomes large. So imagine that this Fi itself is some, say, firing rate times an interval of observation. So if the interval of observation becomes long, for each neuron, the spike count over a long interval can be thought of as the sum over many spike counts over shorter intervals. And so in that limit too, we can show that this X is going to be normally distributed. More broadly, on the many conditions it's true, but it depends also on the correlation. I discussed now situations in which the different observations the noise in them is independent. If it's not independent, it might not be true. So I don't want to go into the details, when is it true and when is it not true. For this example of independent Poisson neurons, it will become true, for example, when the means are become large for each neuron. But let's assume that that's the case. If we assume that that's the case, then
I'm not sure why when F is large, then it gets also normal distribution.
well, because let's think of just one neuron. Let's imagine that you have just one neuron. So a Poisson distribution, when its mean is large, is similar to a normal distribution, but there's a reason to it. The reason to it, again, is that a Poisson variable with a mean alpha times mu can, let's call it m times mu, whereas m is an integer, can be thought of as the sum of m Poisson variables. Can be thought of as a sum of m Poisson variables with mean mu. So if we take m to be large, it's like a large number of independent observations, and that's why the Poisson distribution becomes similar to a normal distribution when its mean is large. Anyway, let's assume that that's the case, that the distribution is normal. Then we can characterize it only by its mean. So we're going to have some distribution of x given theta 2, which has some mean and has some standard deviation. We can calculate them. And that, if we know that it's a normal distribution, that tells us everything about the distribution. And then there's going to be a similar distribution given theta 1. And it's clear where we want to put the decision boundary. We want to put it right here, right? And so, but because both of these distributions are normal, we can calculate what is going to be the probability of error. If theta is, let's assume that theta has equal probability to be theta 1 or theta 2. So if it's theta 1, so there's probability half that it's theta 1. And in that case, the probability of error is the area below this part of the curve. And if the theta is theta 2, then the probability of error is the area below this part of the curve. And under the assumption that these distributions are normal, we can write it down in terms of an error function, a complementary error function. So we can write an expression for the probability of error. And now we remember that all this depends on our choice of W, I, and B. So both these distributions, of course, are actually depending on these parameters. But if we have we have an expression for the probability of error in terms of these parameters, and now we can optimize it. We can find the minimum with respect to these parameters. So this is another approach to optimize a linear discriminator, which can be applied to more general context than the one that I discussed with you here, where we explicitly wrote the likelihood function in this way. In fact, if you try to apply this approach to the problem that I discussed here, there are some subtleties. You will not there are some subtleties if you want to see that these approaches give the same answer, but we will not do it right now. But we will go back to this approach. Well, maybe we'll start it today, or maybe in the next lesson in some other slightly different context. So it's an important approach to discuss. Now, the next topic that I want to discuss briefly, you will do most of it with Neta, is linear decode, the linear estimators. And let me use a slightly different notation now, just because I want to be consistent with my notes so that I will not make confusing mistakes. So I will call now the observations R instead of N. So we have P of R given theta. And as we discussed, our definition of a linear estimator is an estimator that can do something like this. And as we've already discussed before, when you consider estimators, you have to decide what is your goal, what do you want to optimize. For discriminators, it's much more clear. You want to minimize the probability of error. But if you do an estimate, you have to decide what weight to assign to an error. So, as usual, we will consider minimizing the mean square error. So we can write this as the average of theta hat minus theta square. And what are we averaging over? We are averaging over the joint probability of R and theta, which can also be thought as the probability of the prior, or the probability of theta, multiplied by the probability of R given theta. Okay, so I will not do the calculation. I just want to write down the result. And so the result has the following structure. So the result has this following structure, that the optimal weights are equal to some matrix multiplied by a vector, which I need to define. Okay. I will also write the result for B. So maybe I should put here optimal. So the B optimal is given by this expression. So what is written here, this is the mean value of theta over the distribution of theta. And this is the mean response from each neuron, again, over this joint probability of theta and R. Now I need to write down this matrix and this vector. And this is a vector. So Cij is the covariance matrix of the responses. And U is a vector whose elements represent the covariance of the elements of R, the responses, with the stimulus. Now, and whenever I write an average, I mean that it's an average over this joint distribution of the stimulus and the responses. So the optimal estimator depends not only on the way that the responses depend on the stimulus, but also on the prior of the stimulus. Now, does this remind you of something, this expression? Which perceptron? So we discussed two types of perceptron early in the course. We had binary. If you will look through your notes, or if you remember what was the other one, then you will be able to say that It's the linear perceptron. It's very reminiscent. These equations are very reminiscent of the equations that we got for the linear perceptron. Now, it's not a coincidence. So let's discuss for a moment what is similar and what is different between the problems that we discuss right now. There is one difference if you look at the equations, which is very technical, and this is the fact that when we discussed the linear perceptron, we did not include a term like this, B. But this is technical. We could have done it. We could have defined our linear perceptron as one that has a B and just go through the math, and then we would get something very similar to what we got here. Okay? So this is not very interesting. The more interesting thing is the definition of the problem. Why is there a relationship? Well, there we discussed a function approximation problem, right? We had some function of multidimensional inputs. So it's a scalar function of multidimensional inputs, and we wanted to approximate it by a linear function. Here we're discussing estimation. We have some probabilistic response of the observations based on some scalar theta, and we want to estimate theta as best as possible. Why is there a relationship? Well, you can think in this case about the specific and actually not very interesting situation where the R's are deterministic. So you could think of a situation, so you could imagine a particular situation where there's no variability in the responses R. The R's are some linear, or non-linear, the R is some function of theta, deterministic function of theta. And then in some sense, we're just dealing with a question of, I provide you the R, and you want to tell me what is the theta that has generated this R. There's probably a unique answer to that question. So this is a certain function. There's a certain function that associates with the R's a theta. And your goal is to approximate then this function as best as you can with a linear function. So in that particular case, the linear estimator is really just trying to approximate as best as possible in the mean square error sense the function that relates theta and R. But here there's another layer of variability which is not coming from the distribution of the thetas, which is this one. So this is a bit more general than what we did when we discussed the linear perceptron. Now, what I would want to do is to give you one example for the application of this result.
Is it any different than the linear perceptron of the noisy teacher?
It's very similar. It's almost the same. And you will see when you do the calculation that it's almost the same. But we did not discuss a linear perceptron with a noisy teacher. We discussed linear perceptron. Ah, I see. Okay, I forgot. So I think that it's very similar. Okay. So what I want to discuss for a moment is to apply this case for the problem for the example that we discussed here, independent Poisson neurons. So I can erase discrimination, and I can keep this and erase this. So again, doing the example of independent Poisson neurons. Linear estimator for independent Poisson neurons. And so what I called here R is now N. And if we just want to calculate, in order to find the best weights and the best B, we need to calculate these quantities. So that's what I want to do. So I already wrote that Ni, the mean of Ni, which appears here and here, is Si of theta. And now what I need to do is to write down the mean of Ni and J. And again, this is a mean over the joint distribution of R and theta. So so let me first write down the mean of Ni and J over for a given theta. Okay? So suppose that I choose a particular theta. Under that, the distribution of responses, well, maybe I should write here n. What does this mean? So what is it if I is different from j? It's a product of two positive non-negative numbers, so it doesn't make much sense that it's 0. It factorizes. Why? Because we assume that these are independent Poisson neurons. So if I is different from j, this is fi of theta, fj of theta. If I is equal to j, we have to be careful, because now we have here the same neuron. It's not two independent quantities. So we're actually asking what is the mean of n square for a Poisson neuron.
You know the variance.
Exactly. So what I can do is to write down it as the mean the mean squared plus the variance. So the mean squared is still fi of theta times fi of theta, right? It's fi square of theta. But I need to add the variance. What is the variance? Fi of theta. So the conclusion is that I can write this whole thing as fi of theta times fj of theta, which takes care of this and of this part, plus some added contribution if I is equal to j. So I will write it using the Kronecker delta functions, which is 1 if I is equal to j, times fi of theta. Okay, now this is just averaging over the neural variability. That's not what we need in these expressions. Here the expression is also averaging over theta. So this is the average of this over theta. And therefore, what I can write down now is that Cij is it okay when I write here? You can see it? Cij, I need to take the average of this thing over theta. So I will get now fi of theta, fj of theta averaged over p of theta. What this means when I write something like this is very simple. It's an integral over theta, p of theta, times fi of theta times fj of theta. So it's a one-dimensional integral. And plus delta ij fi of theta averaged again over p of theta. Now I also need to subtract the product of the means. And the product of the means are simply the average of fi of theta over p of theta times the average of fj of theta over p of theta. But let me rewrite this where should I do it? I will continue, I think. Okay, I will keep this just for reference and work on the top half of the board. So this is equal to, I will just reorder the terms. So I have here fi of theta, fj of theta over p of theta minus fi of theta, fj of theta, both over p of theta, plus delta ij average of Fi of theta over P of theta. So this expression is nice. In this particular example, this expression has a nice, we can think about it in a nice way because we can think about it as including two terms. One of these terms, this is the variance or the covariance of the response of neurons I and J just because of the distribution of theta. Right? Here there's no, the Fi of theta is just the mean response. So this kind of term would exist even if the neural response was deterministic. If neuron would give us, instead of a spike count, would give us a rate, which is the F. Right? This is this part. And then there's an additional part which came from the neural variability, right? Where did this come from? This came from the fact that the response of each neuron was variable, so we had this variance of the response. And this is really what is coming from the neural variability. So you see that this covariance matrix has a part which is non-diagonal and has to do with the distribution of theta. And then the neural variability, because the neurons are independent of each other, because the neural variability is independent in all the neurons, enters only in the diagonal element of the covariance matrix. And let me just, for completeness, write down UI, the elements of this vector. So, well, it's whatever it is. It's the so once we choose theta, the mean of R is simply Fi of theta, and then we need to average over theta. So we'll get here something like this, and then minus the average of theta and the average of Fi of theta. Okay. לבריאות. The rest of the discussion on linear estimators we will do with Neta, and what I will do in the next bit more than 5 minutes, 7 minutes, 8 minutes, is discuss a somewhat new question, still on discrimination and estimation. So we'll focus on discrimination, but what I want to discuss is situations in which the variability between the different in the different observations. So we imagine that we're observing the activity of some neurons. Let's imagine that the variability in these neurons is not uncorrelated. Okay, given the stimulus. Of course, it's always correlated given the stimulus, but because of the stimulus. But conditioned on the stimulus, let's imagine that the noise is not independent in the different neurons. We can imagine many reasons why that might be the case. I think that we discussed it in the past, so I will not ask you, but just mention some of them. We could imagine that there are some inputs, common inputs to many neurons that encode the stimulus, which are not related just to the stimulus, related to some other internal state of the brain or some other stimuli, and these affect the neurons jointly. So there are many situations, and also if we just record in the brain under some well-defined condition, we record the activity of different neurons, we often find that there are some correlations between some of the neurons. Maybe they're connected to each other, and that mechanistically causes some correlations. So we want to begin to develop some understanding of how correlations between neurons affect our ability to decode some quantity from the neural activity. And what I would just like to do in the next few moments is convince you that it is a rather confusing question, that we can come up with different arguments why having correlations are good or why having correlations is bad. So let me write down a title. Neural correlations, detrimental or beneficial? Okay, so I just want to think about some simple, very simple examples and see what happens in each one of them. So actually, right now, so I will talk about Fisher information, which is, as we know, related both to estimation and to discrimination. Let's imagine that we have n IID neurons that whose response depends on some variable. And so IID meaning that they have the same distribution conditioned on the variable and they are independent of each other. So what happens in that case to the Fisher information? How does it depend on the number of neurons? It's a sum, so it's a linear. So J is proportional to n. So in this case, when we have more and more independent neurons, we can improve our estimate in a way which is mathematically described by this dependence. It means that say if we do an estimate, then the mean square error will go like 1 over square root of n. If you do discrimination, you have this expression for how the discriminability depends on the Fisher information and on n. Now, in this example, if we have n identically distributed fully correlated neurons, how would the Fisher information depend on n? Fully correlated, by fully correlated I mean that all of these neurons give in each trial exactly the same answer. So it will not depend on n, right? I mean, we don't gain anything from observing a second or third neuron. One of them tells us everything about what all the other ones are telling us. So J independent of n. So in this example, and this is usually when people start to think whether correlations are good or bad, that's the first thing that they say. Having uncorrelated neurons means that we have more and more independent observations, and therefore we can improve our discriminability or estimation. But I want to convince you that that's not always the case. So let's just imagine that we have two fully correlated neurons. But their response are no longer identical, as in this example. So with different responses. So N1 is going to be equal to some mean F1 of theta plus some variable part, and N2 is going to be equal to some other function of theta plus delta n. But let's imagine that the delta n is the same in both neurons. Okay. Well, then I claim that even though the noise part of the response is identical in both neurons, that's actually good. Why is that good?
But why would they be good?
I don't know. It's just a hypothetical example. I just want to point out.
No, mathematically, I mean, if the effort is additive.
Well, yeah. So okay. So there are some subtleties. There are some holes in what I'm doing, in the sense that we think about it as a continuous function and these integers. So let's imagine that our responses are actually continuous numbers and not integers. And then we could imagine that this is some function of theta, this is some function of theta, and then we have some noise which could be Gaussian, for example. So imagine that you have two observations, one with this mean, one with this mean, and with some added Gaussian noise which is identical in both observations. Okay? It's a bit of an idealization but I just want to think about what that means. So in that case, I claim that if I want to estimate theta, my situation is actually very good. Can you tell me why? I can subtract. I can take n1 minus n2, and this is if the noise component in the two observations is a completely always identical, then the difference between the responses is deterministic function of theta. And as long as this function, the derivative of this function with respect to theta is not 0, meaning that f1 prime of theta, f1 prime of theta is different from f2 prime of theta, actually the Fisher information will be infinite. Okay?
For them to be fully correlated, f1 has to be a linear function of f2, right? So we don't
No. So when I say correlated, I don't mean correlated as due to the theta. I'm talking now about the noise conditioned on theta. So this can be any function of theta. What I'm talking about now is some added noise, which is for any given of theta response is this is the mean, and there is some added noise. Okay? So
for them to be fully correlated, they have to be linear functions.
fully correlated, conditioned on theta. So this is, in order to say that they're fully correlated, conditioned on theta, I don't care how their means depend on theta. I just care about the variability.
I would just say that.
No, but it's a very important point that somehow.
Okay, so let's set theta to be
So
constant.
when theta is equal to 3,
Okay.
this neuron has some mean response, this neuron has some other mean response, and each neuron is distributed around, has a response which is distributed around this, and the second neuron has a response which is distributed around this. And when I say fully correlated, what I mean is that the difference between the response and its mean is identical in both of the neurons. If neuron 1 happens to give us 3.1 instead of 3, and neuron 2 had to give us 5 on the mean, then neuron 2 is giving us 5.1. And when neuron 1 is giving us 2.8, neuron 2 is giving us 4.8. Okay, so that's what I mean by that it's given theta. That means that delta n is always identical in both neurons. I can subtract, get rid of it, and I get some observation which is noise-free. If I have an observation which is noise-free and still depends on the theta, I can use it to read out theta precisely. So the whole goal of this exercise was to this very somewhat strange example, because it's not easy to imagine how in a neural system you will get this situation, but it's just to point out that now I show you an example where you have observations, and the fact that the observations are correlated allows you to have very good discriminability. Okay? Whereas in this example, the fact that they were fully correlated did not allow you to do it. But the key, you can probably see what the key to the difference between these two cases is that in order for this to work, the response of the two neurons to the stimulus had to be different, right? Which was not what we assumed here. Okay, but all I want to do is to highlight the fact that this is a subtle and complicated question, and that the answer for what correlations are doing in terms of our discriminability or our ability to estimate has to do both with the mean responses as a function of the stimulus and the structure of the variability. Both are important, and we'll investigate this in more detail in the next week. Okay.
Why is that? Why is there information?
Well, because when the response is deterministic and does not depend on and still depends on theta, that's what happens. You can look at the expressions, for example, for Poisson neurons for the Fisher information. In the limit where the okay, we need to. It will take me a few more. I think too much time to explain this mathematically, but this is what happens. It's clear that you can. It's clear that if you have a deterministic function of some stimulus theta, some deterministic function, and I tell you what this function is, you can achieve zero variance of an estimator, right? Because if you have the observation, you can tell immediately precisely what is theta, meaning that the variance of an estimator is zero, and based on the Kramer-Rao bound, this tells us that the Fisher information has to be infinite. Okay. לא, הוא לא אסטימטור לתטא, אבל מה שחשוב זה שהוא לא, אין בו רעש. הוא איזושהי פונקציה של תטא שהיא לא רועשת. אם היא לא רועשת, זה אומר שאם אני מסדר לך מה הערך של הדבר הזה, את יודעת להגיד בוודאות מה הוא תטא. כי יש פה, למה שלא תדעי? זאת אומרת, אם יש איזושהי תלות, אם את יודעת לסרטט את התלות בין תטא ל-F1 של תטא,
את יודעת מה כן,
כי מוסיפים, אבל אני מסדר לך מהו F1, F2, את יודעת להגיד בוודאות מה הוא תטא. ההנחה היא שאנחנו יודעים את זה.
גם אם השיפוע לא היה אחד.
אנחנו יודעים את הפונקציה שלו.
גם אם הייתי... כן, כן, גם אם השיפוע היה 3,
יש פה תוחלת על פני שני משתנים. אחד ההתפלגות של תטא ואחת ההתפלגות של R given תטא. כל זה רק לתטא נתון ואנחנו צריכים למצא על תטא.